看着是不是天黑了？实际上非也。实际上现在是2021年8月22号的下午1点30分，但天已经黑了，因为发布了河南省的暴雨预警，经过了720特大水，我们这个地方官员估计都吓尿裤子了都。前几天明明什么晴空万里，他妈照样播报预警啊！现在溜溜球真他妈的制造业真他妈朝着制造强国去了。我小时候他妈2.5块2块钱买个溜溜球，他妈睡眠好久。看这破溜溜球，真的垃圾，睡眠他妈2秒钟。真他妈菜！我知道，真的就让我想到。根本，你比如说，我当时在卡塔尔的时候买的那剃须刀，阿曼产的那剃须刀，同样是吉列阿曼产的，我还清楚的记得有阿曼产的，还有那个阿联酋工业园，在阿布扎比的还是对，就好像就是阿布扎比的工业园产的。我用了那一个刀片带上一个刀把，我用了他妈7、8个月都没坏。等回到中国，他妈我放着不用它都能坏，我操！我他妈服了。咱中国基本上就是用1个星期它就锈了不成样了，就没法用，就弄就没法用了，你只能换1个星期。这现在也是我们制造业强国制造的这东西就这个样子。虽然它不贵，对吧？但是它跟十几年前、15、16年前那不对，不是15、16啊，16、17年前那个制造水平相比，对吧？它也真的是很垃圾。哎，我无语了，好吧，行吧，不说了。我这最近买了好多教材 ，CAT 的笔译什么什么的都还没做呢，赶紧给做一做啊，这一这。另外这个 MINE4404真他妈快把我逼疯了嘛，他妈的服了，行吧，一点一点搞啊。我估计我的效率不高，就是跟没直播有关系。不会吧？他妈开个直播就播不成啊？Given stress tensor, OK. 锁。Excusez-moi。我这个龟龟这下的有点大呀，我操！这他娘的，别把我家又下漏水了，我操！Stress given stress tensor。 stress on surface. Stress on that surface.
Write it down.
Normal vector.
S equals to sigma times n. This is just the representation. Now, this formula works when I have the unit vector. Well, unit vector, you know that unit vector has the length of 1. And in here, I need to make my vector, let's say, normalize that into the unit vector. So just in here, unit vector positive, it actually it has this formula, nx squared plus y squared plus z squared, and unit vector has a length of 1. So if you haven't been given the unit vector, this is the formula to normalize yours. And basically, it's the vector with length 1. Alright, so we are given outward normal vector of 1, 3, 5. We need to normalize that into the unit vector. In here, I'm writing that in capital N so that you distinguish between the N and, let's say, unit vector and the one that I already have. So it is 1, 3, 5. I just have that in mind that this is not a unit vector. What you have to do is that you need to normalize that. Right? Just substituting this into this formula.
What?
It's going to be 35. I'm using this formula in order to convert that into unit formula is 1 divided by the length, so it is actually length. Divided
什么意思？我操！
times 1, 3, 5. Now this one is the normal vector. Now we need to apply the formula to S. S.
有他妈这么写的吗？我操！
So you know that this is the formula. Now I have the vector, I have the tensor, the stress tensor has been given to me. I found this one. I'm going to multiply these two in order to get the stress vector. times. Of course, this is the, let's say, resultant stress vectors in training. So we are going to have the magnitude of 6 divided, so it's going to produce for us a vector, right?
它乘它乘它6，它乘它加它乘它6，它乘它乘它。
You can just get the, you can isolate the factor.
散的搞死冇 OK。 21
6, 21, 5, and you know the unit for that is in Pascal. In Pascal, this one is the stress
天死
vector on the surface. So you have 3 components of x, y, and z. And this is based because of the assumption that we are getting one line, which doesn't have a depth, so we don't have the third dimension. For next problem, we are going to work with the 3D, and after that you can have a little bit of break, and then we are going to continue with today's tutorial. Before going there, any question? All good? Yeah. Sorry? So, okay. This one? Yeah. So, yes, actually, it can, for 3D, it can be a little bit tricky. So, what you mean is that sigma y is in this direction? So, okay, here, 3D representation in 2D is quite hard. So, if I go with this one, I go, this is x, this is y, this x and y on one plane, and this is z, right? So this one and this one is our x's. So sigma xx normal, sigma xx normal, and the tau's are perpendicular to one another, depending on the direction they're going. This is x, this is y. The tau in this one, so it's going to be, if I, again, now your question is with y, right? If I go with the y is this face, right? Or let's say this face. So for y, if I go like this, it's going to be my normal. My normal is sigma yy. Now, if I go in a direction of x, which is my first tau, which is my first shear, each face has 3 components, 1 normal, 2 shear. If I go along the x-axis, I'm going to have tau yx in this one, and then I'm going to, let me just making sure that it's all accurate. And then if I go along the z-axis, like this, it is going to give me tau yz. So this one, tau yx, this one, tau yz, and this one is sigma yy. So is that clear? Oh, okay, okay. That's actually, I can go with this one. Is that making sense? That's actually Great observation. Thank you so much. But yeah, let's say negative, positive. Are you happy? Actually, it's for that's actually great for more accuracy. That's right.
妈的，洋人的逻辑是什么？没点好
So,
笑
any other question?
我他妈一点也觉得不好笑，也不觉得好笑。
So, guys, remember question number one? Question
他妈
number
的
one
漏
was
水吗？我操！
inclined, getting the stress on inclined plane based on 2D. Now for question number three, we are going to do exactly the same in 3D. And now I'm quite sure that you're all familiar with this because, first, I don't know if you remember a good deal of your solid mechanics, but this was actually stress transformation.
这怎么会是2D 的？我他妈的奇怪了！
It's the easiest, it's the fastest, and you can get the accurate magnitude at the end for each of the components. Yeah, we're just going to do that. So again, for first question, if you remember, we had the biaxial stress combination. We had the along the y-axis we had sigma 1. Along the x-axis we had sigma 2. This is exactly similar to our problem number 1. Let me just for refreshing your memory, I'll show you what I'm talking about. So this one. This problem was in 2D, right? We had x and y, and we are just using the equilibrium of the forces. This one, sigma 1 and sigma 2, they're different magnitude, and we didn't have anything for sigma 3. So the first assumption is that this is biaxial stress. Having that in mind, that for this problem specifically, the vectors are showing inside the structure. So it means that we are in compression. So everything should be positive. Sigma positive, sigma 1 positive, sigma 2 negative. The only difference between problem 1 and problem 3 is the direction of this vector, meaning that the third problem is in tension. So we are, instead of shrinking our volume, we are just going to expanding our volume. It's just something to consider based on positive and negative. Anyway, this is, if I want to write down the axis, this is going to be my y-axis, this is going to be my x-axis, and for z-axis, I have all components 0, 0, 0. In this problem, we need to, so the stress tensor at point P of a solid body is given as minus sigma 2 in the normal, diagonal, let's say, of this matrix in a normal position, sigma of 2, sigma 1, we don't have any shear stress. Also, we don't have any stress on our third axis, on our z-axis. Now, what we are going to do is that we are going to consider the rotation in here. So the new axis of x prime, y prime, z prime chosen by rotation of 30 degrees about the z-axis. Now, we need to determine the stress tensor x prime ij in the new coordinate system. So this is another way of asking to answer the question number 1, but this time in 3D. Now the only difference, as I said, is the negative sign. So negative is the sign of tension. That's why I just changed the vectors of my stress in the negative direction. So the only difference between negative is the sign asking about ij in the new coordinate system. 30.
操你妈！你
Now, what you're going to do is that going to consider the rotation in here. So the new axis of x prime, y prime, z prime chosen by rotation of 30 degrees about the z axis. Now we need to determine the stress tensor x prime ij in the new coordinate system. So this is another way of asking, to answer the question number 1. What is sign in 3D? Now, the only difference, as I said, is the negative sign. So negative is the sign of tension. That's why I just changed the vectors of my stress in the negative direction. So the only difference between this question number 1 is that. So we have the initial coordinate system was x and y in a solid black. I hope you can distinguish this. This is the black, this is the blue one. Hopefully, similar here. So what we are doing, and then the z-axis is coming out of the plane. And for that reason, I have this, again, 2 coordinate systems. If I take a look at them in that manner, I'm going to take this one as my z-axis, which I don't have any value on it, and the rotation is going to actually happen along this one. So if I'm going to rotate my initial, let's say my initial coordinate system, if I call it x, if I call it y, and this is z, the new coordinate having 30 degrees of difference. So something like this. So this is x, this is x prime, this is y, this is y prime. And then I'm going to get the relations between the old coordinate system and new coordinate system component by component. Then I'm going to end up with the rotation matrix. Once you get the rotation matrix based upon that angle you have, 30 degrees, you can actually get the stress much more easier on inclined surface in 3D. So there's a formula for that. It's quite easy and it's based on your solid mechanics. So the transformed stress, sigma prime, is the multiplication of reverse matrix into normal, let's say, rotational matrix into the sigma, the original sigma, which has been given to us, this one, to the transpose of the rotational matrix. So you can write it down like this. So original stress, rotational matrix, and you know that they're all in 3x3 matrices. You're going to rotate you're going to transpose the rotational matrix. It's easy to just going to change the direction of the rows are going actually to be seated in the columns. It's quite easy. And then the new stress space based upon this rotation can be actually calculated easily. Stress space based upon this rotation can be actually calculated easily. Okay, so we're going to start with the directions. Well, this is the old coordinate. and this one is the new coordinate based on the angles we are obtaining. So we are going to get the cosine between x and x prime. Then we are going to get the cosine. This is actually quite important how we're writing that down. It's going to be cosine between y and x prime. Cosine in this area, we are going to write cosine of z and x prime. So it is actually it's basically the cosine angle between. So it's going to be cosine x and x prime, cosine y and x prime, cosine z and x prime. And here it's going to be cosine x and y prime, cosine y prime, z and y prime. This one cosine x and z prime, cosine y and z prime, cosine z, and this is going to be, this bit is going to be our rotational matrix. I'm just going to write it down. Cosine x, cosine y, doesn't matter whether because you're going to get only the angle. You can easily write it down. Like this. Considering your I'm not going to do that one by one. I just want to show you what is the difference. So the cosine between x and x prime. What is so? Assuming that this is x, this is the rotation. What is the cosine in here between x and x prime? 30 degrees. That's right. So the first one is cosine 30 degrees. Now, what is the cosine between x prime and y here? Between these two. Sorry? Yes, that's right. It's 60. So this one is x, this one is x prime. X, y, z, x prime, y prime, z prime. So z and z prime, they are all aligned, so we're not changing anything. But once we are getting that, cosine y, this is our initial y, and x prime, we had 30 degrees in here, 90 minus 30 is going to give us cosine 60 degrees. Now, what's the difference between cosine, x prime, and z? This is the reason why I make this thing for you. That's correct. So, if you're going to show that, if you're going to search for that in 2D, sometimes you can't really get that the z-axis is actually 90 degrees. The difference between z and every individual of these four axes, old axis and new axis, has the difference of 90 degrees, or the angle between them is 90 degrees. So that's basically the reason I wanted to write it down for you. So anything with regards to either x or either z or z prime, which is the rotation is happening along that particular axis is going to be 90 degrees. So cosine of 90, is 0. So again, I'm going to write down the rest for you. And if you want me to explain any of them, just let me know, or stay in class afterwards. I'm going to show you by these two coordinate systems. Cosine 90 is 0, cosine 0 is 1. Going to write x is going to be
稍等一下 ，x 轴和 y 撇轴 ，x 轴哎，还真不懂。
we're just going to apply the formula. That formula is sigma prime is equal to rotation times sigma times transpose rotation. For the transpose, basically, if you want to transpose, you're going to change just the rows and columns. This one is going to be, I'm going to put, this one is going to be this. Just a different arrangement, that's the only, just for a small review. Original state of our stress. One, the rest of the components are 0. And then the transpose. The multiplication and so I already assume that you know how to do the matrix multiplication, and please do that by hand, not by using MATLAB or Excel. It is quite painful, I know, but it is actually quite necessary for at least for the exam to do that yourself. So I'm going to write down the first element. the shear element of this first axis is going to be 312 sine 30 cosine 30 minus sigma 1 sine 30 cosine 30. And last element is 0. Just this conversion. The reason for that is because I want to compare that with our first problem equations that we achieved. So the first shear component of my y-axis, 2 sine 30 cosine 30 minus sigma 1 sine 30 cosine 30. My normal sigma y. And we don't have any z-axis, thankfully.
什么鸡巴意思呀！我操！
This is our resultant. However, in here we have a normal stress. You know that is this diagonal. We have this one normal y. This is normal x, and we have two shears in here. So first shear and second one. If you just go back to your first problem, you can actually compare this one with our normal n prime. It's going to be exactly the same apart from one difference. You remember what was that difference?
方向变。
The direction, guys. First question was in compression. This one was in tension. So the positive and negative. So if you just go and compare the two equations, you can, apart from the positive and negative, everything else is exactly the same. So that's the reason why I highlighted this one. This is for our normal stress, this equation. If you change the directions, if you change the positive and negative based on the compression tension, it is going to be exactly the same. And this one is actually normal to inclined. And what does that mean? Normal to inclined is based on that, we are considering that. So this is for this problem number 3, this is our inclined surface. If I put that along the x prime, so y prime is actually what I'm looking for actually. It's going to be my normal to the surface. And the shear one is this one, which is equal to what I used to have, t prime, and this one was n prime. This one is going to be x prime. So if I go and take a look at my resultant in here, I can actually easily write it. So this one is actually my sigma y prime, which is equal to sigma y prime that I acquired from first technique or first method. In other direction, well, in the tension. And these two are actually my shear. So it is tau yx.
我他妈的吐了！我操！
Symmetry is going to be exactly the same. So it's going to be
他妈的，为什么我觉得这个现实时间过得很快，而这个电脑这个视频时间过得很慢？
Making yourself familiar with both techniques in order to get the stress on incline section. This one is actually quite easier if you are happy with if you can do the matrix multiplication class. Otherwise, the other technique also gives you very similar numbers. So again, just to remind you what it was along that. So that was on one side. And then this was anything along this space is going to give me shear, which are represented by this. Okay, so this one is normal, these are parallel and impartial. Alright guys, you want 500, right? So let's all come back to one. With that, maybe.
Фотографка samtidigt med bäst på stress. Ja. 怎么还有半个小时呀？靠你妈的！干什么呢？说不能服。
Alright guys, let's continue with problem number 4. I'm going to go a little bit faster because we don't have a lot of time for the rest of the problems. We have 4 more to cover, but thankfully the most important ones were already covered. Alright guys, for this one we are going for principal stress and directions. You know that in principal stress it means that we have only normal. In certain direction we are having only normal stress with no shear, and that's what we are calling the principal stress. And there are ways to get those directions, and we are going to do that in this problem. So in certain, as I said, in certain direction, you're going to get the normal stress with no shear. It's going to give you the principal stress. And then, so we are talking about 3D. That's why you're going to have principal stress in 3D. Let's just take a look at the core sample. You already seen that now. It's actually a little bit bigger, but doing the job. If we are going to put that in compression, let's say 400 megapascal, this is the stress, of course, not the force. So we have already considered the area. If we have the, let's say for z-axis, we are going to have 100 megapascal in this direction, in z direction, and for the confining the stress all around this area, we are going to have 50 megapascal. You're normally doing that in pixels. And just if I magnify this thing, I'm going into the volume, let's say, volumetric element. Just imagine I'm magnifying that inside, not on the surface, because on the surface the stresses are going to be different. Inside, I'm going to have this volumetric element. Again, like what we had, what we already explained, along the y-axis, you can see that we have 50 megapascal. Along x-axis, again, we have, because we have confining. Based on our shape, it's both the same, but if you had true triaxial, you could have different magnitude in one of the faces against the other, and our z-axis in here is 100. So first of all, we are going to just, in our mind, we have, for y-axis, we have 50 megapascal, for x also 50, for z we have 100.
操，这个问题我昨天才看过呢，我又忘了。Problem.
So I'm just going to write it down for you. Sigma z equals 100 ampere. Sigma x 50 ampere. Sigma y 50 ampere. I can easily write down
限量的都。
So it's 50, 50, 100. Now, you're showing principal stress with other symbol, the secret symbol that's
不对呀、你这个面儿，这旁边的面儿都可以ignore吗？你看他倒车加速修宪法，妈了个逼嘞！靠的！
you're showing principal stress with other symbol, the secret symbol that's
记字儿名，记字儿。Principal stress. Principal stress and direction. Direction.
we have 1, 2, 3, just as representation of principal stress. Sigma 1, sigma 2, and also sigma 3. So principal stress we normally use these symbols. And also we have this rule that sigma 1 bigger than sigma 2 and sigma 3. So if I'm going to write that in that order, so initially I'm going to have principal stress state. Shield. Sigma equals to sigma 1, sigma 2, sigma 3. Now I need to order what I have in here. Okay, that's sigma 1, sigma 2. Therefore, sigma 1 is going to be my 100 in here. Sigma 2 is going to be 50. Same as sigma 3. Now, writing in a terms of principal stress is going to be
那这狗妹，这走妹啊！
sigma equals this one is my biggest one. Just putting that up. 100, 50, 50. Okay. So stress next. Now I changed that, but I need to consider the direction. I need to write principal direction. Now, you know that for the first one, we acquired that from here. So the direction is actually 0, 0, 1. So it is actually, it's giving you address to how to find your 0, 1, 0, 2, 0, 3.
我受不了啊！我他妈必须得睡一会儿，他妈困炸了。